Hello and welcome to this video on identities that is just going to continue our discussion from last time. So we're going to finish up section 3.7. So again, you should, if something in here is not clear, you should send me an email or read the text. So these formulas are, of course, all found inside the textbook, but the reason I'm making this is because sometimes it's more helpful to have somebody talk you through it than read it. So we're just going to finish section 3.7. And just like I said, the section is just a shotgun blast of identities. So we're just going to continue just with this barrage of identities. And most of these identities you should not memorize. I will tell you which ones you should memorize and which ones you should not. But anyway, let's just dive right in. Here are some identities. These are called double angle identities because there's a double angle inside the sign. So you take this x value and double it. And so if you do that, if you take sine of twice an angle, that's the same thing as twice sine of the original angle times cosine of the angle. And if you take cosine of double an angle, that's the same thing as cosine squared of the angle minus sine squared of the angle. These two formulas here you should memorize. The reason you should memorize them is because they come up so often they come up pretty regularly in Calculus 1, I suppose, but in things like Calculus 2 and things like differential equations, maybe Calculus 3, they just come up all the time. You should just know them for classes like that. So these two guys you should memorize. They will not be on a formula sheet. This tangent one you should not memorize. I don't care if you have that memorized, but here it is. Tangent of twice an angle equals twice tangent of the original angle divided by 1 minus tangent squared of the angle. And of course, if you want to derive this formula here, you can always just take sine divided by cosine, do a little algebra, and you'll get this twice tangent x guy here. Okay, so memorize the first two. Don't memorize the third one. There are a couple of equivalent ways of writing this cosine of 2x. And again, you would either have to have these guys memorized, what I'm about to show you, or just be able to derive them yourself. So here you go. So here are a couple of different things you can note. Cosine squared minus sine squared. Well, sine squared plus cosine squared is 1. Right? That's one of the Pythagorean identities. Sine squared plus cosine squared is 1. That means that cosine squared is 1 minus sine squared. If you just shift that sine squared over. So that's all that happened here. I replaced a cosine squared with a 1 minus sine squared via the Pythagorean identity. And so I end up with 1 minus a couple of sines. So that's an equivalent way of writing cosine of 2x. 1 minus twice sine squared x. So you should know that. But I wouldn't memorize it if I were you. I would just be comfortable with transforming this original guy into this guy down here. And equivalently, I replaced a cosine squared with a 1 minus sine squared. But since cosine squared plus sine squared is 1, you could also write sine squared as 1 minus cosine squared. And that's all that happens in the second line down here. I replace a sine squared with a 1 minus cosine squared, and I end up with cosine squared minus 1 plus a cosine squared. So in this case, I get a couple of cosines minus 1. Sorry, a couple of cosines squared minus 1. So in your textbook, you will see cosine of 2x written in all three different ways. So you should be comfortable with the three different ways. But again, if you're comfortable with the first way, then it's just Pythagorean identity to get you to the other two. So here are the double angle formulas. So here's the same kind of caveat that we have always. You cannot just make up your own identities. Here is an identity that I see with some regularity, I suppose. You cannot just pull the 2 outside. So you cannot say that sine of 60 degrees is twice sine of 30 degrees. Right? You can't just pull constants outside of a sine or a cosine. So these guys are bad. So just to illustrate how bad it is, let me show you how the universe collapses if you're allowed to do this. So we all agree with this, that 1 is cosine of 0. I think we also all agree that 0 is the same thing as 2 times 0. So suppose now that you were allowed to pull that 2 outside, then now you would have the 2 outside times cosine of 0, but cosine of 0 is 1. And look, you've learned that 1 equals 2. right? So if you make up your own identities like this, you will collapse the mathematical universe. You will get contradictions like this all the time. So again, use only the identities that we have and valid algebraic manipulations. If you find yourself using a formula that's not a consequence of something on a formula sheet, there's a very high probability you've done something wrong. So here's an example. We already could get sine of 120 degrees already, but here's how you can use the double angle formula to do it. 120 degrees, I hope you will agree, is 2 times 60. And so sine of twice an angle is twice sine of the angle times cosine of the angle. So I can just fill that in here, and I end up with, yeah, that 2 cancels with that 2. And so what I'm left with is a root 3 over 2, which is what we knew to begin with. So there you go. Okay, so we have double angle formulas. So you can also, of course, have half angle formulas. And so here they are. Sine of x over 2 equals this guy, plus or minus square root 1 minus cos x over 2, etc. So I don't need to read these to you. These formulas you should not memorize. When you're in calculus, your calculus professor may or may not have you memorize these. But if it were up to me, if I were your calculus professor, I would not make you memorize them. So I'm not going to make you memorize them now. You should just be able to use these guys. And yeah, one thing I want to note here, the plus or minus here is solely determined by what quadrant x over 2 is in. Right? Because sine is positive or negative depending on what quadrant you're in. So if you knew, for example, that x over 2, your angle over 2, lived in the third quadrant, well, sine is negative there, so sine of that angle would have to be negative. So you would choose negative square root of this stuff, right? So the plus or minus is there just because of quadrant location. So you should decide what quadrant the angle is in first. In this case, the angle is x over 2, right? So think about what quadrant x over 2 is in to predict whether your answer should be positive or negative. And the half angle formula for tangent has a couple of equivalent formulations, neither of which include a plus or minus, which is nice, so you don't have to make a choice. So the book will write tangent of x over 2 as either the square root plus minus guy or these two fractions. Okay, so those are the half angle formulas. So we already can get cosine of 15 degrees by using 45 minus 30, but let's just hit this with the double angle guy. So cosine of 30 divided by 2 is plus or minus here, but we already know that 15 degrees is in the first quadrant, so we can just go ahead and choose the plus, and we just fill it in, and this is what we get. Yeah, that's what we get. Anyway, so you'd have to leave it like this. Okay. For some reason alright, whatever. That's what it is. Okay, so here's another example using the half angle formula. Let's find sine of alpha over 2 if I'm going to tell you that sine of alpha is 3/5, and I'm going to give you a location of alpha. I'm going to say that alpha is between 2 pi and 5 pi over 2. So in other words, alpha is between 360 degrees and 450 degrees. So alpha is in the first quadrant, but it's made it through one full rotation. Okay. So, so since alpha is between 2 pi and 5 pi over 2, you can divide this entire inequality by 2. And that's all I did there. So 2 pi divided by 2 is pi. Alpha divided by 2 is, of course, alpha over 2. 5 pi over 2 divided by 2 is 5 pi over 4. So the reason you do that is because now you know the location of alpha over 2. Alpha over 2 is between 180 degrees and, what's this, 225 degrees. So in other words, alpha over 2 is in the third quadrant. So in the third quadrant, sine and cosine and things like that are negative, right? Tangent is positive. But anyway, you have a location for alpha over 2, so you can predict whether or not sine or cosine or tangent or whatever should be positive or negative. So since we're trying to find sine of alpha over 2, we now know alpha over 2 is in the third quadrant. Sine is negative there, so our final answer should be negative. Okay, yeah, so sine of alpha over 2 is negative. So we choose the negative option from the formula. Sine of alpha over 2 is the negative version of square root 1 minus cosine of alpha over 2. So of course now you're kind of in a quandary because what's cosine of alpha, right? If you don't know that, how are you supposed to get a value here? So how do we find that? Well, we know sine of alpha and we know the location of alpha. So once you know any one trig value and you have a location, you can find any of the other 5 trig values just like we did last time. So that's all we're going to do. We have cosine, so we have sine, so let's just find cosine. Well, if you have sine and you want to know cosine, you would presumably use this equation. So sine was 9 over 25, is that right? Sorry, sine of alpha is 3/5, and so when you square that, right, sine squared, you get 9/25 plus the square of cosine equals 1. So you scoot that 9 over 25 over, take the square root, and you learn that cosine of alpha is either positive or negative square root 16 over 25. So cosine of alpha is either positive 4/5 or negative 4/5. But we know alpha is in the first quadrant, right? You go a full rotation, but you're back in the first quadrant. And cosine is positive in the first quadrant. Therefore, cosine of alpha is the positive version of that, 4/5. Okay, so just to review here, right? This is the equation that we want to fill in. We know that sine of alpha over 2 is negative square root 1 minus cosine alpha cut in half. So if we could just find cosine of alpha, we could substitute that value in and we will be done. And that's what we did, right? We got a value for cosine of alpha. So here's the original equation. I substitute in 4/5 and I get negative square root of a tenth, which is negative 1 over square root of 10. So there you go. There's an application of the half angle formula. Okay, the next 4 identities are called product to sum because, as you may notice, it takes a product and turns it into a sum. Right? So not a terribly creative name here, right? It does exactly what it says it does. These 4 identities you should not memorize. You should just know how to use them. Here they are. You can read them, I suppose, so I don't need to read them, but this is what happens. So in the first case, if you want to take sine of something times cosine of something else, you turn it into a sum that looks like this, a sum of sines. Where in the first case, the sine has a sum inside of it, and the second sine has a difference inside of it. So again, on your next exam, you will have a formula sheet. These 4 identities will be on there. So don't memorize them, just make sure you know how to use them. So here's the kind of question you might see in your homework or on an exam. Here is a product. Can you rewrite it as a sum? Well, sure you can, because you have a product to sum formula, and sine times cosine, the formula is given like this. So capital A is t squared, and capital B is 12 degrees. So we just plug those guys right in. And there you go. You've taken a product and written it as a sum. These identities here don't show up in Calculus 1 terribly often, but they do show up in Calculus 2 and beyond. Sometimes they make integration way easier. Integration being a calculus concept. Okay, so we have product to sum formulas, so we also have sum to product formulas. Here they are, right? If you have a sum of sines, you can rewrite it as a product. In this case, a product of a sine and a cosine. If you have a difference of sines, you can rewrite that as a product of a cosine and a sine. If you have a sum of cosines, you can rewrite that as a product of cosines. If you have a difference of cosines, you can rewrite it as a negative product of sines. So you can take a sum and turn it into a product if you so desire. You know, again, you should not make up your own identities. So here's an identity that is made up with some regularity, I suppose. So don't do this, right? This is kind of a shock collar moment, right? If I see you doing this, I wish I could just um, shock you or I don't know, give you some sort of negative reaction to seeing this. But anyway, you just can't make up your own identities. This is not true. A sum of signs turns into a product of, well, what does it turn into? A sum of signs turns into a product of a sine and a cosine. So here's the kind of question you might see. Rewrite this guy as a product. So it's a difference of signs. So here's the difference of signs formula. And here's the work. So in this case, x is 6t, y is 4t. So you add the two guys together and cut in half inside the cosine. Subtract the two guys together, cut in half inside the sine. And you end up with twice cosine of 5t times sine t. And that's it. So again, I know this section just kind of is overwhelming with identities, but focus your energies where they should be focused. You should not be memorizing most of these. You should just make sure you can do the questions where the formulas are applied. So make sure you can answer questions like this with the formulas in front of you, and don't try to memorize them. So have a good weekend and see you.